do, I would love to welcome Dr. Zhang, all the way from Wisconsin, to introduce Alex, our first presenter.
Can you hear me okay?
Yes.
Okay, that's great. So I will give a brief introduction about Alex. I'm Alex PhD advisor, and Alex is a second year PhD student in soil science from Kansas City, Missouri. She started her degree at Oregon State University and recently moved with the lab to the University of Wisconsin-Madison. She is primarily interested in pedology, or the science of soil formation, with a framework that looks at soil as a system of biogeochemical interactions. She's interested in how disturbance impacts soil systems, as well as how to use new technologies to improve soil analysis and mapping. Additionally, she is passionate about environmental education. At Oregon State University, she was the coach of the soil judging team and continues this work at UW-Madison. So her primary research topic involves understanding the formation, spectral properties, and disturbance impacts on endosols, or the soils typically formed from volcanics. In addition to working on her projects with the France Research Foundation, Alex also assisted with the development of an interactive map of the Cascade-Siskiyou National Monument, where some of her data will be showcased on the new France website. So now let's welcome to present her research results.
Yes, hello. Can everybody hear me okay?
Yes, I can hear you.
Yes.
Awesome. Okay. Hi, my name is Alex. Thank you for the introduction. I'm a second year PhD student at the University of Wisconsin-Madison, and I am so excited to share this fun side project that I started this summer, where I explored the topographic and ecosystem controls on soil properties in the Cascade-Siskiyou National Monument. But first, I want you to imagine that you're going on a scenic drive through the Cascade-Siskiyou National Monument. So you start on Highway 66, and then you go down south on some service roads. And as you head south, you look out your window and you spot this beautiful Douglas fir forest. It's dense and lush and full of trees. And you keep going south, and the ecosystem doesn't change much. You're just surrounded by this never-ending sea of green. But then all of a sudden, something clears up. Unlike the Douglas fir that surrounds this hill, you're looking at an oak savanna where you have more grasses than trees. You get out of your car and you look around. Everything other than the vegetation seems the same here. You go home and look up the two sites. They have nearly the same aspect, elevation, geology, land use history, and climate, but for some reason, these two slopes host completely different ecosystems. So you might be wondering, why are these sites different? Well, as a soil scientist, I can confidently say it's because they're built on different foundations. So today I want to talk about these two sites, how and why their soils differ, and what that can tell us about the relationship between soils and our monument's biodiversity. So first I'll talk about my methods and the data we collected. Then I'll share some katinas, which are old school soil science illustrations that help us understand the soils at our two sites. And then I also had the privilege of collecting a lot of data, so we were able to make quite a few interpretations. I'll share the results from just one of those interpretations, wrapping it up and talking about how our soil carbon is stored along our slopes. So first, our first step is deciding where to dig once we have our two sites. So if we're curious about soils, we can't just pick up a little bit of soil off the ground. We have to dig a soil pit. And if we're good soil scientists, we're going to dig a few because our soil changes with our hill slope position. So we decided to dig 4 pits at each site, one near the summit, one near the foot slope, and then 2 in the middle, one kind of in the upper back slope and one in the lower back slope. This is what we call a topo sequence or a katina, and it's one of the oldest methods for soil science research. So basically, we're keeping everything constant except for our topography, so we can understand how our landscape position impacts our soil. And since we have 2 sites, we can now understand both ecosystem and topographic influences on these properties. So here are just some pit locations laid out. My landscape data is quite coarse, so this is a little bit of a rough topo map, but we can just see that our points are laid out. These are our Douglas fir points, and then our oak savanna points all fall along a slope. And if you know anything about soils, you also know that their chemical, physical, and biological properties change as you dig down. So soils form layers that we call horizons. And so while we're in the field, we figure out where we change between horizons, and then we sample from each horizon. Instead of sampling at like a specified depth of 25 centimeters or 100 centimeters, we sample where the soil changes. And then when we're at the soil pits, we collect full field descriptions. So we look at our observable physical properties like our soil texture, which is how much sand, silt, and clay we have, or the color of the soil, or its structure, the shape it forms naturally. And then we take our soils home for a number of analysis techniques in the lab. And I have to thank Matt McClintock from the Bureau of Land Management for going out and helping us pre-dig these soil pits beforehand. That was extremely helpful and saved a lot of time. And while in the field, we also had the pleasure of using this as a learning opportunity for some students at the Oregon State Soil Judging Team. So they helped dig out the pits a little bit deeper. And while they were there, they were able to learn how to describe those soil pits and collect samples and data about these soils. So it was a great learning experience. Yeah, so thank you to them. And we collected a lot of data. So not only field measurements, but also a number of lab analysis. Big thanks to my undergrad student, Max, who did some of the more tedious ones for me. We did X-ray fluorescence, electrical conductivity, texture, pH, and a number of others. Most dear to my heart is mid-infrared spectroscopy, which I actually just did here at UW-Madison. So we were able to use models that we've developed in our lab to predict properties that would otherwise be too expensive or tedious to do on our own on a small budget, such as soil organic carbon, which I'll be talking about later. I don't know. Okay. Sorry about that. So what did we learn? What are the soils actually like? So first, I just want to compare two profiles from these soils, both on the lower back slopes of the Doug fir and the oak savanna respectively. So the first thing you'll notice about these soils is that the Doug fir has this 10-centimeter layer at the top of moderately decomposed organic materials, which is a mix of moss, litter, and other materials we expect to find in a coniferous forest. Meanwhile, you'll notice that we don't have anything like that in our oak savanna. We just hit straight mineral soil. And the next thing you'll notice is the amount of rocks. So our oak savanna is much rockier. There's gravels that you can clearly see here, whereas the Doug fir has very few rocks in the profile. Something that you can't really see, but you can definitely feel when you touch the soil is the amount of clay. Our Douglas fir has a little bit less clay in it than our oak savanna. And then the most important property, I would say, is that our Doug fir soils are very, very deep. We never hit bedrock. We just kept digging. Whereas in oak savanna on the lower back slope, we hit the bedrock at 40 centimeters. So because of that, our difference in soil depth is pretty significant. So now I want to show what these soils look like along a hill. So this is a transect of the Douglas fir along a hill slope. Again, this is with some pretty coarse data, but these are the actual colors of the soil. We tested these in a Munsell color book, and then we converted the colors into RGB. Though you'll notice they're a little darker than the photo because these colors were taken with wet soil, which is standard for soil classification. But notice how all these soils are dark and deep throughout, which is indicative of having a lot of broken down organic matter. But near the foot slope, we have a lot of dark and deep stuff that's accumulated. And that's because our organic materials have moved down the slope through erosion and accumulated in our foot slope. All of our soils are relatively thick and deep, but it is, very evident in our foot slope. Additionally, these little gray circles were put into R to represent our percentage of rocks in each horizon, and you'll notice that there's not that many. So if you know your vegetation, soils like this totally make sense for the area. Our Douglas fir generally prefers thicker, well-aerated soils. Meanwhile, our oaks are very different. So Oaks can thrive in rocky and stressed soils. So here we have our oak savanna, which you'll notice is quite a bit rockier. You can also see that our lower back slope is shallower, stopping at 40 centimeters, and we have this little indent in the hill. Also, all of these soils are darker. If you know soil horizon, you'll also note we have this BT horizon right here, which is just a way we indicate that our soil has accumulated a lot of clay that's weathered in place. So these soils are clayey and rocky, but our soil at the foot slope has a lot of our AB horizons, which means that a lot of organic materials also in our foot slope have accumulated and created a thicker soil. So this photo is where our lower back slope pit is. And you can see that kink in the landscape a little bit, and that's where the material starts to accumulate. So we believe that there was some kind of large-scale erosional event in the past based off of the landscape and the soils that we see, some kind of mass wasting, which has led to this thinner, less survivable soil for Douglas fir. That's just an inference on our part, but it kind of makes sense with the topography and the soils that we see. And so now I want to get into talking about one analysis we were able to do with the data we collected. So you've probably heard of soil carbon. It's a very hot topic these days. Basically, our plants take in carbon dioxide, and as they and other organisms break down in our soil, some of that carbon hangs out for a little while in a more stable pool. So most people think a lot of carbon is stored in our trees, but that's actually not where most of our carbon is. So estimates of how much carbon is stored in soil actually varies quite a bit, but it's somewhere around 80% of terrestrial carbon. And soils are the second largest carbon sink in the world behind the ocean. So carbon stock is a rough approximation of how much carbon is stored. So I just calculated this by taking a look at our organic carbon, which we estimated with mid-infrared spectroscopy, how dense our soil is, how much of our soil horizon is actually soil and not rocks, and then how thick a particular layer is. And we just multiply that all together and we get a number that represents our soil carbon stock. And our difference between our profiles is pretty significant. So I think this is pretty cool. So in this figure, the darker color represents having increased soil organic carbon stock along the hill slope. So along our oak savanna, you'll notice that the color doesn't change much along our profiles. We have a little bit more carbon stock at the surface, but it's relatively homogeneous. But as we move down the slope, we notice that in our eroded areas, our back slope, we do have a slightly darker color throughout the profile. Meanwhile, let's take a look at our Douglas fir. So you'll notice this has this really striking pattern right here. Almost all of the carbon in the Douglas fir is limited to that really thin organic layer near the top. And then it very quickly drops off to having much less carbon lower in the profile than our oak savanna. And I think this is just a really interesting insight and reflection of our ecosystem dynamics and how our soils are related to our ecosystem and our ecosystems are related to our soils. So I want to remind you of this photo. So, remember most of our organic matter in the Doug fir is in this like thin layer at the top that's really, really dense with high carbon stock. But meanwhile, in our oak savanna, we don't have that organic layer at all, but we still have organic carbon throughout the profile. It's just a little bit more uniform. And there's a few reasons. The first, if there was historically an organic layer, it's probably been eroded off, right? Because we have a lot of erosion at this site. But the second is actually because of vegetation. So Douglas fir is dropping a lot of litter, but that litter is this kind of acidic stuff that's really tough for our decomposers in soil to break down. But meanwhile, our deciduous litter tends to be a little bit easier to break down. And we're not full of trees, but instead our savanna is blanketed in grasses. And grasses have really deep, fine roots that penetrate deep in the profile and break down relatively easily. So we end up having more carbon deeper in the profile versus this like concentrated dense layer on top. So if we were solely interested in the protection of soil carbon, we would want to mitigate erosion in Doug fir, but we would want to protect our grasses in oak savanna who are depositing that carbon annually as the roots die off. So just some takeaways for that. Our soil properties at each site are influencing our vegetation present, but our type of vegetation is also influencing our soil properties, including our soil's ability to store carbon. And then carbon distributions are more uniform in our oak savanna, but they're concentrated in thin carbon-rich layers in our surface for our Douglas fir. So that's just one insight we can glean from this data. There is a little bit more. If you remember, we collected a lot of information and we were able to get some other interpretations. And that data, along with those interpretations, are soon to be integrated in an interactive map, which is going to be coming to the Friends website. So you can use this QR code, though it's not super awesome on a phone. Let me paste the link in the chat. This is a draft of our map. Basically, almost all of this work was done by an undergraduate student named Joe, who works for us. We're still fixing some bugs and making some changes if you went to our demo, but I'm really proud of what he's done, and I just kind of want to click through and show you what this looks like. Can you guys see my screen?
Yeah.
Okay, awesome. So we have both a story map and this interactive mapping system, and this uses all publicly accessible data, both soil data, climate data, all sorts of stuff. So here we have the Cascade-Siskiyou Monument, and this map right here shows the mean temperature at the monument. We can also look at things, you might be like, I don't know my way around. We can add on the highways, we can add on service roads, we can add on like areas people mapped at. We can also look at things like our land cover or our elevation. And then we can look at soil properties. So Cascade-Siskiyou National Monument is really diverse in terms of soils. So it's a really great place to look at soils, and you can explore that diversity. You can even click around and get really specific details about the soil. So, and then if you click on Story Map, we have some information you can look around. So yeah, if that interests you, it's great. This will be on the Friends website soon. Yeah, feel free to look around at that. And yeah, thank you so much to everybody for watching this presentation. Thank you for letting me come on Zoom. I wish I could be there in person. Thank you to the Friends for funding this research. Thank you to, Yakun, but also Matt McClintock, Dr. Hans Stroh. This could not happen without Hans, my lab mates, and the people who showed me how to use equipment. This has been really fun, and I'm just so glad to have been able to do this project. It just reminded me why I love soil science. It's simple, but it's super, super fun. Thank you.
They can't see you and maybe necessarily hear you. I'll take questions from the audience, and I'll also field some questions if anyone has them on Zoom. But raise your hand if you have a question for Alex. Yes.
This is maybe kind of a simple question, but as a non-geologist who's interested in soils, what were like the dimensions of your soil pit and how long were you spending at each soil pit? What goes into a single pit in this type of research?
No, that's a great question. So I have a slide about this in my spare deck. So describing a soil pit, we did full soil classifications. So this is what like a soil mapper would do. And typically we try to dig to at least 100 centimeters. Sometimes you just can't do that. But we were using this as a teaching experience. So the time we spent was kind of dependent on education. But you go out to a soil pit, you dig the pit, you delineate your horizons, and then you take some samples and we do tests. So we can do field pH. We also take a look at our texture. So we feel it in our hands and just get an approximation before we go into the lab. We look for signs of weathering. We look at what kinds of rocks we have. This can take a long time or a little bit of time. This is a Munsell color book. So this is like a standardized way to get soil colors. And then we do full classification. So we have a system of classifying soils very similar to like the system for species, domain, eukarya for biology. So we ended up doing this for soils as well. So quite a long time, couple hours per pit usually, but it depends on how many people you're with and how much they're arguing.
That's great. Thank you, Alex. There's a question from Leah online. Is there any other reason why the different in vegetation types? Why are there different vegetation types other than soils?
Yeah, so the main thing we know, like that's the main difference that we can infer. There's probably some difference in there might be some difference in fire regime. As far as we know, it's relatively similar, but like we know oak savannas and Doug's fir do kind of have different fire regime. But if you look at the data in the area, if you look at like the geology maps, the climate maps and everything, it's all relatively similar except for the soil. That's, our main defining difference.
Great. Anyone in the audience have a question? I've got a couple more on Zoom here. Just raise your hand if you do. Russ is asking, was the soil map source from the NRCS soil survey of Jackson County area?
Yeah, so it's the Surgo data set, which uses the soil survey of, the whole United States. So for the Cascade-Siskiyou Monument, it was for California and also for the map for California and also for Oregon. All the other stuff we used, we did by ourselves. But
Great. I got another question here from Hema. Similar to Russ's question, how did your soil pits compare to the Surgo data?
It's relatively similar. Our mapping in Oregon is a little bit coarse in places. I mean, Surgo in general, that data set is, it's very good and very helpful, but it's also broad. But it's relatively similar. So if you are familiar with soil maps, in our Oak Savanna, there's this soil series called McKnoll. And McKnoll looks kind of a lot like our back slopes, and it's mapped in the area. Same thing. We have the Pinehurst soil series on the foot slope of our Doug fir. It pretty accurately matches the map units, but yeah, the map unit, like soil varies so much spatially. You can dig 2 pits 10 feet away and they're going to be different, but on the map they're going to be the same. So, it was actually more similar than you would expect, I think.
Wonderful. Any last burning questions? Paul.
I wonder if you could say a little bit, and maybe the next presenter is going to say more about the vulnerability of soils to disruption. If I understand, most of the life is in the A horizon. And I noticed in the conifer forest that was relatively shallow, even though the soil went down a long ways to bedrock, the A horizon looked fairly shallow, such that with severe logging or road building or mining, is it likely that the soil would die?
Yeah, so one of the things we calculated was susceptibility to erosion with the revised universal soil loss equation. I didn't make a figure for that, but the Doug fir soils are a little bit more susceptible to erosion just with the USLE equation. Part of that has to do with the slope at the particular site, but also like the particle size of the materials, things like that. Grasses tend to hold on really well to material to prevent erosion, but they were not super dissimilar with USLE, but the Doug fir is a little bit more susceptible to erosion.
Thank you.
Yeah.
Anyone else? Let's give another round of applause for Alex. Thank you, Alex.
Yeah, thank you for having me.
Just give us a sec. We're going to get switched over to our in-person presenters and get started again. Just so I don't pull up the wrong one. You're going to
I'm just really surprised, like, that's what it's
I didn't screw anything up. We're good. Okay, I think we're all set. We're going to welcome Dr. Karen Mager to introduce our next presenter.
Hi, everybody. It's so nice to see everyone tonight. It is my pleasure to introduce Andrea Osbon tonight for our second talk. Andrea began her work with me to research wildlife within the monument near Interstate 5 back in the summer of 2024, actually, and has been an invaluable member of my crew over this last couple of years. This generous research grant from Friends of the Monument supported her continued work on this project during her senior year at SIU, and she recently graduated with a Bachelor of Science in Environmental Science and Policy, a minor in math, and a certificate in wildlife ecology and conservation. And she is currently working at the Ashland School District. I have really appreciated Andrea is someone who's very no nonsense, can do attitude. You want something done, we're going to do it. We're not going to make a lot of drama. We're just going to get the work done. And it's something I've really greatly appreciated about her. She's a really skilled naturalist, great at identifying animals, curious about how they spend their time, fun to be with in the field. And so she's been a really steady and positive contributor to this research. And that includes fun time in the field, but also looking through millions of photos and videos that occasionally have animals in them, but mostly just have waving tree branches in them. So I really appreciate her, and I'm excited to hear what she has to share.
Every single time Karen introduced me, I try not to cry. All right. Like Karen said, my name is Andrea Osbon, and I will be talking to you guys about some pre-construction wildlife camera trap monitoring for the wildlife overpass in the Cascade-Siskiyou National Monument. So before I even start, I would first like to thank the Friends of the Cascade-Siskiyou National Monument for this grant. This is my second year receiving this grant, and I'm truly honored every single time I get to step and do research in such a beautiful place. This year, funding allowed for my time this summer to be able to do this research, new camera traps to be added to our research, and also supplies for those camera trap mounts. I'd also like to thank the SOU camera trapping team for all their help this year. I truly would not be standing here today unless it was for them and for everything they do. You want to try to get that away? Yes.
Get that away and check our online audio real quick. Sorry about this.
We might be good. I
Okay.
think it's working.
It should be working. Sorry about that.
There we go. Okay.
It's awesome. We'll see the kid. Sorry about it.
Okay. Now to get into some vocabulary and some information so you guys aren't confused during the talk. If you're sitting here, I hope you've heard about the wildlife overpass that will hopefully be built on mile marker 1.7 right before the California border. A wildlife overpass is a bridge that allows species to cross over the highway rather than through the highway and get hit by a car. ODOT averages about 6,000 deer and elk collisions per year, and we are currently in a deer and elk collision red zone. Now, if you live here, you know we hit a lot more than deer and elk, highlighting the need for this overpass. Along with the bridge, 2 miles of fence line on each side will be added to create a makeshift funnel to hopefully allow animals to go where the crossing is and actually cross. As of 2024, funding for this project was awarded to us, but ODOT is still working with federal highways to get everything signed and the money actually given so that we can start construction. The second image up on the screen is of a camera trap. A camera trap is a wildlife trail cam that is put in a lockbox, mounted wherever you want it, and locked so no people steal it. So I'll be talking about camera traps a lot, and I'll also be talking about captures. It's a camera. I'm not going and trying to capture a black bear. We are getting pictures and videos from the camera that we then use for our data. I want to also highlight that in this presentation, I use a lot of we statements. While I am standing up here alone, presenting my findings alone, none of this project is my own. Everything was done directly with the SOU camera trapping team, and all the data that I got and all the images are directly from them. So to get into the species we monitor, the SOU camera trapping team has been monitoring since 2021, and we have a total of 18 different species that we monitor. All of them are mammals except for one, which is the wild turkey, and this is due to these species being the most effective when the wildlife overpass goes in. So the monitoring area, the image you will see up on the board is a map of the I-5, which is in red, our cameras, which are in pink, the pink dots, and then the Cascade-Siskiyou National Monument outlined in teal. This is a 10-mile corridor of I-5 with a total of 38 cameras in various habitats and elevations that allow us to monitor all 18 of those species. Now to get into my project specifically this time. So I split my project into two categories, the continuing of monitoring the wildlife overpass site itself, and then adding cameras to specific areas. So the continuing monitoring of the wildlife overpass allows us to complete our second year's worth of full data. Like I stated before, this is my second year getting this grant. And last year I was able to do a seasonal wildlife analysis of the site. And this year has allowed me to have 2 years worth of data for that seasonal analysis. And then also my second part of my project was adding cameras, specifically to create a multi-camera monitoring system for culverts. This is when we have a camera that is located inside the culvert, as the video shown above, a camera that is located at each entrance site, and then a reference camera. This allows for a full view of what species are using the habitat around and what are actually using the culvert. A culvert creates a whole other habitat that, depending on how the species are comfortable, will use or not use. The biggest factor that we found is if an animal feels safe in a culvert, which then they will use it to cross more safely than actually going through I-5, so they will go under I-5. I also attempted to add fence line cameras on that 2 miles of fencing that will become the funnel. Sadly, on the south side, it goes into the California border and state, so I couldn't add the cameras there. But I was able to add 2 cameras on the Oregon side. Sadly, the way we mounted these cameras, none of the data will be used in this talk, but I do highlight where those cameras are located. Now to get into where exactly I am looking at. The 2 maps that you see on the board are existing and additional cameras added this summer, which is the furthest map, and then the future wildlife overpass site, which is directly above it. You will have a zoomed in look on where exactly it is, and then a reference of the I-5 and the Cascade-Siskiyou National Monument. If you look to the existing and additional cameras map, you will notice that I have 2 sites that are located actually outside the Cascade-Siskiyou National Monument, which might seem odd because this is a Cascade-Siskiyou National Monument talk. The reason for this is we have heavy monitoring in the south within the Cascade-Siskiyou National Monument and at the crossing site itself. But the effects of this overpass will be seen far beyond where the overpass is built. Not only is there 2 miles of fence line to change animal movement, but animal movement will be differed all the way up the 10-mile corridor of I-5. So understanding the movement that's happening in the north will then help us understand how drastically movement in the south is changing. So you will also see in that existing and additional cameras, there are 2 different colored icons. The additional cameras are labeled in yellow, and the already existing cameras are labeled in gray. My first site, which is located outside the Cascade-Siskiyou National Monument, is known as Steinman, with a total of 4 cameras that were already existing at the site and 2 cameras I was able to add this summer. My next site is known as Siskiyou Pass, with a total of 3 cameras. 1 was already here when we started, and then 2 cameras that I added this year. And finally, this location is located right at the edge of the Cascade-Siskiyou National Monument, and this is where I added my 2 fence line cameras, 1 on the east side and 1 on the west side of the highway. Again, none of this data will be used for this talk. Hopefully, in coming years, we will be able to show you some of those pictures. Now to get into the future wildlife overpass site. At this location, we have a total of 4 cameras that monitor the site. This is SOU 8, 9, 10, and 11. SOU 8 and 9 are located on the west side of the highway, almost mounted on the exact same tree. And SOU 10 and 11 are located on the east, about 130 feet apart. This is relatively a small area we are monitoring, but the more we monitor this area, the more we understand the importance of this site. So the continuing monitoring of this site allows us to understand a normal species movement currently in the area and allow us to have a before image of data for when the wildlife crossing goes in. Understanding how these species are moving now can then show us how they are changing their movement with the wildlife crossing. This area is also very biodiverse, with the Mariposa Preserve right next to this site, and is a key site in the Cascade-Siskiyou National Monument for its biodiversity. From these 4 cameras, we have captured 11 different species out of the 18 species we monitor. Now to get into some of my data. So above me is the crossing site seasonal analysis with capture rate located on the y-axis and each species located on the x. Each season is color coded to then be shown with each species to show how many times we are seeing the species in that season. We have 1 species that we only saw in 2 seasons, and this was the cougar in spring and fall. This species was captured at SOU 8 and 10. So we are seeing this species on the east and west side of the highway. We had 3 species that were seen only in 3 seasons. This was black bear, California ground squirrel, and wild turkey. The California ground squirrel and black bear were not seen in winter, and this is due to them lowering their movement during those colder months, rarely being seen out of their dens. Our 3rd species was the wild turkey, mainly seen in summer and a little bit in spring and winter. We hypothesized that this may be because this is at the end of mating season increasing the movement of this species. These 2 pictures were taken from SOU 8, but we see all 3 of these species on the west and east side of the highway, highlighting the need for this wildlife crossing, which will allow for wildlife connectivity. Now to get into my favorite part, which was the culverts. So we did this in 2 different field days. Sean helped me do this, and he is the one who was actually drilling into the culvert you'll see above. So first, it was kind of figuring out how to mount a camera on a culvert. I don't know if you've been around a culvert in a while, but it's a giant metal ring. I don't really know how to mount something on that. So we first took 2 pieces of wood and sandwiched them on the top lip of the culvert to create a secure base that we could then drill other boards onto, and ultimately was able to drill the camera onto the board that was hanging and then mount it facing into the culvert. Half of our culvert cameras look like this because I added them, and half of them we are hoping to look like this in the future. So now to get into the exact site locations. Again, you will see a zoomed out version of a map that shows I-5 and then the Cascade-Siskiyou National Monument, and a zoomed in version to show where these cameras are located specifically. You will also see color-coded dots. The orange is our inside cameras, and inside a culvert cameras. Our green is an entrance camera, and purple is reference. So the first site, like I said, is known as Steinman. We had a total of 4 cameras here, 1 on the east side of the highway and 3 on the west. Our next site was Siskiyou Pass, with all 3 cameras located on the west side of the highway. Bear Gulch, which is located in the Cascade-Siskiyou National Monument, with 3 on the east side of the highway and 1 on the west. And finally, Bear Gulch Southwest Arm, which is with 1 on the east side and 1 on the west side of the highway. Now I'm going to show you what these cameras are looking at and then what the data was. So this is Steinman, all 4 of our west side cameras, 2 entrance cameras and 1 reference camera. And my favorite camera from this site, which was the inside culvert cam. And we figured out we have a ringtail that absolutely loves this culvert. We have many images of this dude. Just, I don't know what he's doing. He looks like he's just curiously sniffing the culvert. So All graphics for my culverts will look like the one above, with capture rate per 100 days located on the y-axis, and then the camera on the x. I have two things that I want you guys to take away from all of our culvert cameras. You may notice that I don't have black-tailed deer on this slide. This is due to their abundance in the area everywhere, and if I kept them on, all you would see was black-tailed deer. And then also, you might notice that we have a little squishing in our entrance cameras, and this is due to the difference in trap nights for each of our cameras. Trap nights are how long a camera has been activated, and both of our entrance cameras were one of the first cameras we've ever activated. The inside camera is our newest, and you may be able to see all the species colors very detailed. This is due to it having a low number of trap nights. So the higher trap nights a camera has, the more squished look you will see in those bars. The biggest takeaway from this graphic is that we are seeing gray fox through every single camera, highlighting that they very much enjoy this area, not only inside the culvert, but around it. And we had a total of 8 different species captured at this site. For all the culverts, our biggest 2 species that you'll see actually using the culvert are gray fox and bobcat. So our next site is Siskiyou Pass. This is east reference with a wild turkey. This is Siskiyou Pass east entrance with a gray fox going into the culvert. And finally, Siskiyou Pass inside the culvert with a mother and baby black bear walking through. This video is very intriguing because it shows that our adults are now teaching their young that the culverts are a safer way to cross I-5. So for Siskiyou Pass, our 2 cameras that were activated this year was the inside camera and our reference cam. We had a total of 9 different species captured at this site, with 1 new one from Steinman, the wild turkey. You will see again that we have gray fox and bobcat at the inside and entrance of this camera. And you'll notice that the east camera is squished. I want to highlight that we only are really seeing the bear inside the culvert. And so hopefully with continued monitoring, we'll be able to see it moving around the culvert as well as inside. Now to actually get into the Cascade-Siskiyou National Monument. This is Bear Gulch West entrance with 2 coyotes walking towards the culvert. Bear Gulch inside the culvert with a bobcat walking through. And I want to highlight the size of this culvert. This is our biggest culvert that we actually are monitoring. And then Bear Gulch east entrance with black bear walking towards the culvert. The culvert is on my side of the screen. And Bear Gulch and Siskiyou Pass are the 2 culverts that we are actually seeing black bear use the culvert all the way through. And then finally, Bear Gulch east reference camera with a mother cougar and 3 cubs. So Bear Gulch, all cameras were activated within 1 to 2 years of each other, and we see the most uniformed look between all of our bars. This is the hope for our final look of all of our culvert graphs. We are hoping with the continuing monitoring, we will see a full look and understanding of how species are moving throughout the whole area, not just the culverts. From this, we had a total of 10 species captured, with spotted skunk and elk being seen for the first time between all of our sites. Now, you may notice that we aren't seeing gray fox with inside the culvert. We are only seeing bobcat. We don't particularly know why this is. One of our hypotheses is that since the size of the culvert is so big, that these species aren't feeling safe actually walking through the culvert. We hope with continuing monitoring, we might get a better understanding on why we're not seeing one of our 2 species that normally use the culvert using the culvert. And finally, to get into Bear Gulch Southwest Arm, this is our reference camera on the east side with a coyote just walking past. And then Bear Gulch Southwest Arm west entrance with a mouse chasing a bobcat. And here he goes. Now, this is our most extreme difference in activation times, with west reference being one of our first cameras that we ever activated, and our east entrance camera only being activated last year. I want to highlight that even though our west reference camera is so squished, you are seeing coyote so much color, which is showing how much coyotes are using this area. I want to also highlight that we are seeing some interaction with the entrance from coyotes, which is very interesting because coyotes are one of our species that never really go through the culvert. So we also see a very high skunk presence, which has not been seen at any other site, with striped skunk being the most seen skunk and spotted skunk showing a little. Again, you'll see we have gray fox and bobcat again at that culvert. Now to get into my conclusion. This year, the continuing monitoring of the wildlife overpass site has highlighted again how much we need to continue monitoring this site. Understanding the movement of these animals now is going to allow us for a before and after picture on how much this movement changes once the wildlife overpass goes in. This year, I also understood that having multiple cameras monitoring a culvert is crucial in understanding how these species are moving within that area. We are seeing so many different species that we never thought would use a culvert actually using the culverts, and certain species only in that area specifically to use a culvert. And with that, thank you so much for listening to my talk. These are all the people that I truly couldn't have done this without. Thank you, Karen, for all of your nights that you helped me with data analysis about me just dribbling on and on about nothing. Sean, thank you for coming out and risking sparks in your eyes to drill into those culverts. And thank you, I know they're not here, to our 2 interns who helped me collect data this summer. And with that, I'd love to take questions. Yes.
So maybe you could talk louder because I probably missed some of what you said, but what have you got to tell the BLM in relationship to design and implementation for the project, eventual project? Is bigger better or depends?
So what I would tell the BLM for the design of the overpass, I think honestly, my biggest thing is the plants they would put on the overpass. The species need to be able to want to go there. Like, yes, you can have as much fence lining as you want, and you can make it the biggest you want to make it. But if the plants don't make them feel safe, and if it doesn't feel like part of the habitat, they're not even going to cross. So I would think we need a lot of time on those plants. Yes.
Did you see any?
No, go for it. Go for it.
Was there? Have you caught any images yet of Pacific Fisher?
Yes, we have a lot of, we have a couple cameras. They are further north than the Cascade-Siskiyou National Monument, but we have a little feelers out to get some grant money to maybe go in more at the forest places where we have seen Pacific Fisher, but we don't catch them as much as we would like. Yes.
I'm just curious, do you enter all of your video data into iNaturalist?
We use time lapse, and Bernie Bosco, who is listed up here, has actually helped us create a more technical way to go through the images and videos. As Karen said, we have a lot of images and videos that are nothing. She helped with students to create a program that you put all the images into, and it kind of puts a box around if there is a species. Of course, we have a lot of human checking that there's no technical error. But yes, we mostly use time lapse with a little bit of help from other technology.
I'll just add on to that. That's not a publicly available program, so we haven't added. We've got about 18,000 observations.
Yes.
Jack's asking, can we make modifications to improve existing culverts for wildlife passage?
Ooh. I don't think so. Karen, you got any thoughts on that? Could we make the culverts more better?
I mean, places elsewhere with large culverts have been able to put in benches that make it a little easier to travel along the sides of the culverts. Those are typically easier in larger culverts where you're able to have like high and dry areas. Ours are so small, I think that would be challenging.
Yeah,
to-
we might be able for Bear Gulch because it's the biggest, but also Bear Gulch is like, we hate going to Bear Gulch. It's like up, down, up, down. So like any construction there would be hard.
Or just kind of a follow-up to that, are the areas around like the entrances and exits of most of the culverts pretty natural? Like they have a lot of like natural vegetation that's grown up, so the animals maybe already feel maybe they're already pretty well modified from like a landscape standpoint.
Most of them, yes. We do have one. Yeah, I can scroll. Steinman. Steinman is pretty bare. If you look at Steinman West reference, the highway is literally right next to that culvert. So it's interesting that we see so much animal movement, even though there's not a lot of cover. But most of the areas we're having more cover around.
Could you tell me if there are any of the cameras that capture sound?
Yes, all of our cameras capture sound. I just muted everything because it's a lot of wind and trees rustling. We have had a couple that we don't know what the sound is from. We'll have a camera get activated and you'll hear sniffing and squealing, but that's it. So we do every now and then try to see if we're hearing the animals.
Thank you.
Yes.
So, does the monitoring data like support where exactly the overpass will be?
Yes, it'll be at mile marker 1.7. So right before the California border.
I mean, does the data that is your observations of where the wildlife are, does that support, that's a great location for it?
Oh, yeah. The biodiversity of that area is so high that it is a great site for it. They had a total, I think, of 3. This one was the second location because while the biodiversity was great, where it was located is the easiest to also build.
Lisa says, thanks for the great presentation. I'm wondering how the cameras are powered.
Batteries. So many batteries. Yes.
Is the fence line gonna be 2 miles going north and south on both sides of the road?
Yes.
And do you think certain animals will have different reactions to the fence? Will they be benefited more for certain species?
Yeah, the fence line, yes, will be 2 miles each side, going north and south. And I totally think that with construction, we're gonna see a lot of those more nervous species just disappear for a while. Like cougars don't like a lot. Well, we are seeing more cougar interaction with humans, but like if there's a lot of human activity, the cougars most time are like, oh, I don't want to be here. So deer are gonna instantly probably cross the site, and then more of our cautious predators will probably take a year or two to be like, okay, I'm actually safe here and try to cross.
On the like human interaction point, obviously I-5 is a big human presence. Have you noticed kind of like a delay from when you check your cameras, especially like when you install the ones that are, right in the face of a culvert? Did it take like a day or 2 before you actually saw anything, or did stuff just start going through?
I'm gonna ask Sean, what do you think? I think that's 50-50. I think we had some species who just went right back.
Yeah.
Yeah. So we had some species, like I said, more species are skittish than others. So some species were like, okay, there's a camera here now, I guess. And then other species, the ringtail itself, actually, we have a couple of videos of him sniffing around the camera, trying to figure out what the heck it is. But yeah, it was like, it didn't take long though, because like these species know the culvert is safe. So adding one little thing, doesn't really shake them too much.
Do you see like the same individual animals like use the same culverts repeatedly? I like you have the video of the mother bear teaching the cubs and the cougar with the cubs, but especially for the predators that are up like territories, things like that. And then like the second part of the question would be like the culvert or the crossing once it's constructed, it's alter like so like animals learn that it's there, and then does that alter like their hunting behaviors or their behaviors for just something with some animals even like take up residence like on the overpass or
So for your first question, if we are seeing individuals, sadly with the cameras, we can't distinguish. Like we see a couple of deer, like there's one deer with like a cut in its ear, and I'm like, oh, she's back and all that. And with the bear, you can kind of like estimate that that is the same bear teaching its cub. That was one of my things when I first started this project. I'm like, how can we track the individuals? And like, technically we can't. And then how behavioral will change. That's honestly just we're gonna see. There's some of our smaller species that we do monitor, like the squirrels, that might take up residence on the actual crossing site. And deer, honestly, any other way they can cross, I feel like they're gonna take it as soon as possible. Cougars, it allows them to have a bigger scope and easier range to hunt. So we could see shifts in deer populations because of that, but these are all like hypothetical. We don't know yet.
I was thinking like after 18,000 videos or something, maybe you have like names for certain.
We do. We have a couple like it's mainly the deer because they have the most distinguishing like weird features. But yeah, sadly we can't do it. And I think that was my last question. Okay, thank you guys so much.
Welcome, Dr. Margaret, back up to introduce our next presenter.
All right, I hope you're getting excited for this last talk. I think it's going to be a good one. So I'm pleased to introduce Riley. Riley Sutphin is currently a senior at SIU pursuing a degree in environmental science and policy. He's been a really active undergraduate researcher at SIU. I've been lucky to have him work with me on some of the wildlife camera trapping. But he's also done a lot of great work with my colleague, Dr. Hima Hasnarik-Gudapati, on the research he'll be presenting today. And he regrets she couldn't join us in person today, but is online, cheering Riley on from the web. So the work Riley is presenting today started as an SOU summer research project. And we're really grateful to the Friends of the Cascade-Siskiyou National Monument for making this work possible. Riley really jumped into this work at every stage of the project, not just collecting data, but also helping to really think through the research design, troubleshooting in the field, and even got really creative and fabricated some of the equipment that they ended up using for the monitoring. So please join me in welcoming Riley to tell us about this project.
As Karen mentioned, I'm Riley, and I'm going to talk about some of the Mountain Meadow hydrological monitoring that I've been doing up at Parsnip Lakes in the Cascade-Siskiyou National Monument. So why study Parsnip Lakes? It is home to the Oregon spotted frog, which is a nationally listed as an endangered species. It also is an area where you have regulation of both water flow and temperatures in and out of the wetland. And that can impact it feeds into the Klamath watershed. So ultimately that can affect like salmonids. And then it also is an important provider of ecosystem goods and services. So carbon sequestration, other animal habitats, sediment retention, and many more. And then also there is a historical beaver presence in the area. However, they have not been present for a couple decades now, unfortunately. But it's some important context to know. So as far as prior information on the hydrology of the area, we were lucky to meet Charlie Schultz, who had been working to monitor surface water flows through the area. So this is the outlet of the lake on the far side of the screen there, where he's monitoring using a weir. And so we have some flow data from 2021 through 2023, thanks to him. We also have water level variation nearby where that weir photo is taken, thanks to Michael Parker, who is using a staff gauge to measure the water level in the actual wetland. And then we also have precipitation data from PRISM, which uses interpolation interpolation to then estimate how much water precipitation you're getting in the area. And so this is the typical climate for the area, averaged from 1991 through 2020, also using that same PRISM data. And it works out as a typical Mediterranean climate. So in dry summers, it's higher elevation, so it's a little bit cooler than down here in the valley. But then you also get wet winters that have like over 3 times precipitation that you get in the summertime. But obviously, our climate's changing and warming, so it's projected to transition from that cooler Mediterranean climate to more of a warmer temperate climate in coming years. And this is projections through 2094, which is a ways out, but you can see that it moves pretty rapidly into that warmer area. And so this is a plot of the data that Michael Parker was so generous to provide us with. Of some of his staff monitoring. Specifically, we are monitoring the lower Cattail Marsh, which is up towards the top of the plot. And that red dotted line is when the Beaver Dam analog was installed by the BLM. And so essentially what that is since the beavers weren't present, humans went in and were like, let's make a dam and see what happens. And so the idea is to retain more water. And you can see that it did exactly that with the water level shooting up pretty drastically after that installation, which works into a pretty common hydrologic principle, which is the continuity equation. Ultimately, it breaks down to water in and water out, but there's the storage time in the middle of these larger pools. And so when you decrease the water out, like installing a beaver dam analog, your inflow is then greater than your outflow, and your storage increases until it reaches a new equilibrium. But obviously, a wetland is more complicated than a bathtub. So you have additional inputs and outputs. And so specifically for our site, there were 2 surface water inputs, both a north inlet and a southern inlet. The northern inlet is the lion's share of the water for sure, flowing into this system as far as surface water. And then there's a pretty consolidated outlet where that weir monitoring was taking place. You also have groundwater inputs, groundwater outputs that are a lot harder to monitor because they're subterranean. And then you also have evaporation from solar radiation and from transpiration, plants photosynthesizing, as well as precipitation, so rain and snow events coming in. And so we wanted to know what's going on with the marsh with all of these different hydrological fluxes. And so as far as the surface data goes, this is the monitoring data that Hema and I have collected using our weir over the past few months. And you can see it's pretty variable. You go from essentially having more flow out of the wetland to start, and then it slowly goes into taking in more water kind of in the wetter months, but then it dips back down and dips back up. And so there's not really a super defined trend, but part of that has to do with during the winter time, water can be more locked up because it's not fluid, it's frozen, right? So it can't flow into the wetlands. So generally you'll see lower flows during the winter time solely because of temperature. And also during the summertime, the wetland could be fed by groundwater from the previous water year, so when the snow's melting and recharging groundwater. However, this winter, as I'm sure many of you know, was a terrible snow year for us. So this is our snowpack trends. And so the median snow amount, or like snow water equivalent, so essentially how much water stored in the snowpack for this time of year would be about 10 inches, which is that green line, and we are the black line. So we have pretty much none. So it's obviously hard to kind of pull some of these larger trends out of kind of an outlier of a year for snowpack, unfortunately. But that didn't stop us from trying to analyze more. So instead of just having our monthly WEIR checks out there, we also had water level loggers that log both water level or atmospheric pressure, really, and then temperature. And so those take samples every 15 minutes as opposed to our manual once a month. And this is showing both the inflow of the larger stream. The smaller southern stream was such little flow that there was not enough water in it to put a logger in it and have it measure anything meaningful. And then you have the wetland surface as well as the outflow surface, and then rain from that PRISM data set at the bottom. And you can see that whenever it rains, you see a sudden increase in water level, and they are all highly correlated from the inflow, the wetland, and the outflow. And they're all at a similar magnitude, which what that tells us is essentially when it rains, the water flows in and flows straight out of the system as opposed to like recharging groundwater. But speaking of groundwater, we wanted to know what was going on with that. So to do that, we needed to install monitoring wells. So one is a water table well where it's a PVC pipe and it has a bunch of slits in it. And so you can measure exactly where the surface of the water is. And then there is a piezometer, which is similar. You have slots, but only at the bottom. And you drive that into the ground, and it essentially disconnects the water table from the surface water. So like on the near side of the screen above me, you can see like the water level of the groundwater is higher than the surface of the lake, which would indicate that the groundwater is trying to move upward and upwell. And so we installed one surface water monitor kind of in the center of the lake. It's the lighter dot. And then right next to it is also a groundwater monitor. And so those are those two white PVC pipes in that other photo. And then there is one that is kind of up the flow of the lake, which is then kind of to the west. And then there's one to the south, roughly 90 degrees from that. And so the realities of working in the wetland, installing them was pretty difficult. There's a thick vegetative mat. And so normally you're walking on about 6 inches of water until suddenly you're no longer walking on said vegetative mat and you end up hip deep in the marsh. And that's a 6-foot T-post that I happen to be carrying with me. That I was like, well, I'm stuck in the marsh. Maybe I can use the T-post to get out. Clearly that was not the case. Thankfully, I did manage to get off. So, but before we get into some of the data that we collected with the loggers of like groundwater, wanted to cover quick some of the factors that can go into why wetlands change temperatures. And so the first one is climate drivers. So that's going to be air temperature, precipitation, solar radiation. And those are the factors that can change with climate change, as well as like location, latitude wise. The second one would be like landscape and topography. So what's your elevation? How high up are you? As well as like what aspect are you on? Are you on a southern slope, northern slope? And then the third order is a lot more like finer scale, where it's like, what is the surface area to volume ratio of the wetland? So is it like wide and shallow, or is it narrow and deep? Or there's residence time, how fast is the water moving through the system, as well as like riparian vegetation shading. Is there vegetation blocking the sun and shading the water? And so this is temperature data from our for loggers that are in the wetland. And so you see the pretty drastic decline. That's our surface water, is the lightest one. And you can see in the summertime, it is by far the warmest, and then it gets to be by far the coldest. And then the other three lines that are trending a lot closer are the 3 groundwater monitoring wells. And a couple of interesting trends to pull out is that the west groundwater, which starts out as the bottom blue line, transitions from being the coldest source of water in the summer to one of the relatively warmer ones during the wintertime. The wetland itself stays relatively warm the entire time, going from pretty close to some of the groundwater to a fair bit warmer. And then the southern groundwater transitions from the warmest during the summertime to the coldest during the wintertime. And so another way that we can interpret this data is looking at how the air temperature affects the water temperature. And so essentially, if you have 0 groundwater input, your water or your air temperature and your water temperature will be very linked and correlated, as in the top corner. And then if you have some shallow groundwater input, that amplitude goes down. So it's a less drastic swing day to day, but it also shifts the peaks a little bit later. So you end up with a lag. And then if you have deep groundwater, you don't necessarily get that same lag, but it even more drastically reduces the amplitude of those variations. And so this is a preliminary annual variation chart. Obviously, we do not have a year's worth of data here yet, but we will continue monitoring. And so what this shows is the black line's air, and then you have the wetland, which is kind of has a phase shift. So there is definitely that lag, and the amplitude is greatly reduced. And then you have you have the output, which is the darkest green line, and you can see that it tracks the air pretty well as far as both timing and amplitude. And then you have the input, which is kind of somewhere in the middle of the wetland and the output. And then this is the same graph, but with our groundwater temperatures overlaid. And you can definitely see that while the surface waters are way on the downward trend, the groundwater lags behind that by about 60 days, which is very typical for shallow groundwater lags, and also that the amplitude is greatly reduced. And then so that's more seasonal trends. As far as daily variations go, that's another thing to look at. Whereas you have air, which is, a big swing day to day, depending on like whether the sun's up. And then you have the wetland, which is the dashed and dotted line, and it's a highly stable temperature. And then the more squiggly line that goes up and down across the wetland, that's the input. So it averages pretty close to the input. And then the output is a lot more air coupled. So you see during the summertime, it's actually warmer than the wetland it's coming from. And in the winter time, it's colder than the wetland it's coming from, indicating that it doesn't have as much groundwater input or like temperature stabilization as those other two sources. And so again, we're looking to figure out kind of what the fluxes are. And while we don't have quite a year's worth of data yet, it definitely increased our understanding of what's going on in the wetland. And so we can pretty confidently say that this particular lake in the chain is what's called a mixed wetland, where you have both groundwater upwelling into it, as well as downwelling out of the system. And that's helping stabilize the wetland from these large temperature swings. So it's cooler during the summer than it otherwise would be, and it's warmer in the winter than it otherwise would be. And that most likely this water is all just shallow groundwater that is doing this, and that we don't have like any real deep upwelling from like deeper water sources. And I'd like to thank the Friends of the Cascade-Siskiyou National Monument and the Friends Research Fund grant that allowed this work to happen, as well as Southern Oregon University's STEMREX program that was also a funder, the BLM for giving us a research permit to allow us to do this work, as well as Michael Parker and Charlie Schultz for sharing their data with us.
If you run across, or any of the people in your project run across, literature that explains any of the wetland plant distribution by water temperature of what they're growing in?
Considering Hema and I are both not botanists, but that is definitely like something that you can look at, I would imagine. But yeah, it's definitely outside of my area of expertise. Dan?
So the lake used to be more open, or assuming it used to be more open from talking to Michael Parker and the beavers being gone. Was there any data that you looked at before that showed if the temperature of the surface water was more variable before it was covered in vegetation, and now is it more stable?
As much as I would wish to know that, I installed the loggers, this about a year ago, and I would have needed to install them about 25 years ago to know that. But I would be willing to bet that the temperature of the lake would be increased because you do have less vegetative shading, which that is like something that has been studied. So, yeah, my educated guess would be, yeah, it would be warmer.
Do you think the really dry conditions are a good opportunity to see what's going to happen to the wetland over the next year in terms of like recharge into the system?
Yeah, I think it'll definitely tell an interesting story, especially with, the winter before this last one was like an okay snow year. And so seeing how a poor dry year affects the recharge into the lake and like how much groundwater contribution it's getting, I think could be a good way to look at the potentially like, what is it going to look like when our climate shifts in a more permanent fashion towards being hotter and drier. But yeah, it'll be interesting to see as long as we can continue monitoring up there.
Great.
So, here.
I was just going to ask about the frogs,
Yeah.
the Oregon spotted frogs. Just thinking about what is the significance of this research for thinking about their habitat, and do you see any indicators out there in your hydrological research of like, I don't know, conditions that either are suitable for them or potentially threatening for them?
Again, a little bit outside of my wheelhouse, but talking to Michael Parker, they actually like enjoy kind of the warmer waters during the summertime. But of course, it is interesting that like with having the more stable wetland, like you could definitely have some amount of like this Oregon spotted frog doesn't like being frozen solid, right? So having those kind of like refuges for them to hang out during the wintertime could be important. However, talking to Michael Parker, there are not a lot of them left out there. So we do see a lot of frogs, but not Oregon spotted frogs out there, unfortunately.
How'd you identify parsnip lakes in general from the entire monument? And then how'd you identify which of the parsnip lakes to actually start monitoring?
Yeah, so our initial search was mostly using remote sensing. So using the National Wetland Database from USGS, and then also like the land cover, or the Oregon Department of, oh man, I always mess up Dogami's. The Oregon Department of Geology and Mineral Industries has a LiDAR data set of a lot of the monument. So combining that for slope, as well as land cover and where wetlands were, helped us kind of narrow them down to several sites. And then talking to Michael Parker, who's done research in this area for decades, he was more than happy to give us a tour around, which we are very grateful for. And so he allowed us to really hone in on the ecological importance of the site and kind of some of the context surrounding it.
Do you have other teams that are working in this type of study on various parts of Oregon that may have the Oregon spotted frog? And then you could share information with us.
Again, a little bit outside of my wheelhouse since I'm trying to study the hydrology, not necessarily the amphibians, but talking to Michael Parker, I mean, part of the reason they're endangered is because they are endemic to the area, and so they don't really occur a lot of other places, and the places that they do occur have been changed or threatened just due to invasives, climate change, stuff like that. And so like these chains of lakes have changed a lot over the last 20 years, which has impacted them. And it's not necessarily due to like specifically like us going in and doing something, but like the removal of beavers, for example, like definitely was one of the contributing factors to like the change in this lake. So again, it's a little bit all the plants and animals are a little bit outside of my wheelhouse. I'm a water guy, but yeah.
How fairly mapped is the groundwater up for Monument, and like who maps it?
It is not well mapped in general because to map the groundwater, you have to drill a bunch of test wells, and drilling wells is expensive. And so like our wells really only get at shallow groundwater. They're not very deep. So to do like a thorough study of that, it would be a lot of equipment, time, money, and just as far as like resource allocation goes, I don't think that a lot of people are like looking into that. Of course, there are residential wells, and Oregon Water Resources does have some monitoring wells. But again, this is federal land, so like, yeah, it's not super well monitored.
This site a good candidate for a beaver need to be moved from some private property to some other location?
The photo that I had in wrong one. What did I do, Daniel?
There you go. I should get back to this there.
I don't know the screen sharing. I should probably have that. But this photo of beavers is actually a reintroduction attempt to the area. So the beavers were originally like hunted and trapped, and then because of the kind of transition to a more vegetated environment, they were like, okay, well, let's try and reintroduce some beavers and see if we can get back to what it was when the Oregon spotted frogs were more successful. But beavers are pretty finicky about where they do and do not like to hang out. And so the site conditions just weren't right for them at that time. So they moved on to bigger and, better bodies of water. But it'd be neat to try and revisit at some point, yeah. If there's no other questions, thank you.
Thank you.
I'd like to give all of our presenters one more round of applause. Thank you so much. And this is being recorded, so it can be found on our YouTube channel and on our website. Give us a little time to get it up so you can share it with maybe someone who has an interest in one of these topics who wasn't able to attend. You can also chat with our presenters after we wrap up here. If you want to correspond with them more, you can set that up. Yeah, otherwise, just kind of want to give you a quick spiel about just we're gonna have a really fun season in the monument. Lots of really cool topics coming up. Getting ramped up in April, and just want to say that everything that we do is supported by grants and individual donations. As we're faced, there's been federal funding cuts, and that has led to an even more competitive grant landscape. And this is where you could potentially help us. Our programs, including Hike and Learn's Interpretive Rangers, the Info Station, and stewardship efforts all rely on the generosity of individuals. The Friends Research Fund, which supports all of the wonderful researchers you heard from tonight, is entirely supported by individual giving. We are fortunate to have people who care about the monument and step up to support our work. Some of you may be in this room. I actually know that some of you are in this room. And even by attending our events, you are already a big part of that support. We so appreciate it. So if you are interested in giving, talk to myself, Daniel, any of those board members who I pointed out at the beginning, or you can just visit our website at Cascade-Siskiyou.org. But at the end of the day, we are very grateful for this community and your support of the monument and our work. To hear more about what's going on, if you're not already on our email newsletter, that's the best way. And there should be a sign-up sheet out front. Well, thank you. See you next year.